Symposium. Thank you. Well, see, if you get for some complicated task where there are more than one brain region that's involved in processing, then oftentimes you want to know between these brain regions what connects to what, how information is being processed. So here's your answer. That's just the visual system. The use of this diagram nowadays seems to be completely the opposite from what was the original intent. The original intent is to show that there's a great deal of regularity and a hierarchy of these connections. Nowadays, everyone wants to point out that each of these wires has two ends, and information goes both ways. They are all reciprocally connected. So we really don't know which way information goes, one way or the other. So it still remains a problem that as to, can we know, for example, in prosecuting object recognition, that while a certain brain region provides the input to the other brain region or the other way around. There are obviously many methods that were geared towards answering this question. So today I have sort of a proposal. So the question is, can fMRI be used to review the ordering of information processing? Now, this obviously cannot be done if we have to rely on the temporal resolution of functional imaging. But what I want to show you is a possibility. I emphasize this. It's only a possibility that perhaps some of the old tricks that psychophysicists use can be now adapted to this technique, so which allows us to see, or at least measure in some indirect way, intermediate stages of processing, and use psychophysical sort of reasoning to sort of pull out this order of information processing. Right? The essential premises in this is that there is some sort of order. There is some sort of order of processing. There's general progression of the information in the sense that some upstream area depends on the lower stream area for their input. So there's maybe increase the complexity of the features that's being extracted. Or for the purpose of object recognition, there's this notion of increase in terms of invariance and feature invariance. This becomes the most important concept that we're going to exploit for getting some sort of ordering out of imaging data. So this is what I meant. So you have an input image, and then there's some processing site. So that you can think of these as sort of recognition pathway. And these, you might have some sort of top-down influence or modulation or whatnot. But by and large, there is a progressive increase in terms of feature invariance in the following sense. What this network really is that you can see this as sort of a many-to-one classifier at each stage. And I'm giving you some sort of really toy example in this. For example, you might have a stage of detect edges. So all these are edges. At some point, you don't want to know what was the details of what causes this edge. What you need to know at some point is that there is an edge of certain orientation. So in that case, all these being classified into a single output. So all these inputs are then sort of mapped to one output. Now again, maybe if you want to construct some sort of larger structure, you might not be interested in the specific detail, how long this little edge is, but you're only concerned about the organization of which. That means that all these sort of little edge input might be of a different length, would then be sort of the length kind of lost at this stage. So this, if I think of this again, is sort of many-to-one classification. And again, you can do that too. So perhaps not just one orientation of this, but multiple orientation of these would get mapped to one. So you have this a sequence of many-to-one kind of mapping in this type of processing streams, from very simple local feature to much larger and sort of invariant type features. Now, is based on the realization that if you now inject noise into the input, this noise that was injected at the input level would then have a sort of differential impact on these processing stage, and depending on how far away they are from the input. Specifically, you have more graded impact on the side that's close to the input, and you will have more of these all or nothing type of impact to the side that's further away from it. Now, I'm going to go back to this, why this might be the case later on. What now I want to show you is actually the experimental data. So at least if you don't believe the theory, you can enjoy the data. Right? So here's the experiment. The experiment, you fixate at this, this is done in well, the time is done on the 1.5 T record. So the task is simple. Subject are asked to say whether these two pictures are taken from the same scenery. So here the answer will be yes. And here the answer would be no. So when we choose a task of a rather higher level task, so ill-defined task, the idea is that we want the subject to engage, and we don't want the subject to engage in some very low level, sort of pixel level comparison. Okay. Now, you notice we add noise to the stimuli. Noise, the external noise is added to the stimuli in such a way that it matches the spatial frequency spectrum of the stimuli. And the reason we do this is such that the noise, the early visual system will have a harder time, not necessarily very hard, but just a harder time to separate this noise from the signal. And so that this noise is still has its impact as it sort of moves down the processing stream. We add it in such a way that we don't disturb the average RMS contrast. And this is, you've done this sort of weighted sum on the energy, so you get a square root over here, then you would be able to produce it. By choosing this value k, we can change the signal to noise ratio of the resulting image. We use 4 of these signal to noise ratios you can see here. This is the higher signal to noise ratio you see corresponds to a reasonably high performance level. These are all performance level measured in the magnet. So the subject was actually doing the task is correct. And this is second highest, second lowest, setting the performance exactly at chest. So we know that this noise manipulation indeed produced a sizable change in behavior in terms of percent correct. So we're interested in what happened. So this kind of noise manipulation to different cortical regions. So the way that we do this is on a separate session, we actually obtain the functional maps of the subjects. So these functional maps allows us to separate using standard radiotopy techniques to separate different radiotopic area. And then these orange region are done by contrasting between intact object versus scramble, child scramble object. This generally labels the lateral occipital complex region. And then we just take a stroke of pen and draw this area to be arrow and this arrow to be the sort of anterior top arrow or the post-fusiform area. And so that's just by anatomical landmark and concept guessing. But that's okay. As far as we are interested, is that this is the posterior part of lateral occipital, this is the anterior part of lateral occipital. So now let's see what those noise tests, how those noise impact performance. So here's V1. And you can see that the noise actually has absolutely no impact. This is time course. This is evaluated design, and you see that compared to baseline, which is just a fixation, there is an impact. So we turn the picture on, there is some signal, so the brain is working. But the different signal to noise level does not differentiate. Now you go further down the processing stream. Here's V4B, ventral part of V4. We only look at the ventral pathway. You can see that now you start seeing separation. This is the lower signal to noise concentration, second lowest, second highest, the highest. If we go further upstream, now to the posterior part of the lateral occipital, you can see that the separation is not much clearer now. Right? And then if we go even further, down to this posterior region of the anterior region of the lateral occipital complex, you can see it's very clear. So, and this is sort of a summary. So if you plot here we plot signal to noise in log scale and log both signals. You can see that V1 and V2, we see no slope. It's not significantly different from 0, although nowadays the results for this condition at a high field magnet, that they indeed show a sort of negative slope, for which I will not explain why. Obviously there's a reason for that. But at this point it's very low slope, and here you can see that the slope starts progressing increase. Right? So the log steepness of these curve goes up as we move from the low level visual processing area to the higher level processing area. Showing that. Okay, so that's the data. Okay, so now for those of you who don't like periodization, you can. This is the place you leave. And so here is how do we interpret this. What does this all mean, and how are we going to do it? So remember, we have this idea of there must be some sort of increase in feature invariance, going from very simple features to very complex features. The invariance increase, and the reason for this is that we have basically a cascade of these many-to-one classifiers. Now, in object recognition, we talk about invariance. If we move to psychophysics, there is an analogous notion. It's called signal uncertainty. Here's how it works. So suppose you're going to detect a very faint blob of light, but you don't know, for example, in this case, where it's going to be displayed around the display. This is a condition where we have signal uncertainty. Now, the notion of signal uncertainty has been studied almost since day one when people start studying the shape of psychometric function. These are numbers taken from back in the 60s. And these are not even vision. This is audition. So the orange curve plots the human data, typical human data. This is sort of percent correct as a function of signal to noise in log unit of detecting a very well-defined tone. But the task is detection, so you have to say whether there is a tone or there's no tone. Now, if you compare this, so there's nothing surprising with this. You have if the tone is have a higher dB, then of course you're better at detecting it. If it's low dB, you cannot detect it. So that's not much. But I want to draw your attention to the shape of this curve compared to a set of model curves. So here is a model curve of M equals to 1. This is a model where the shape of the tone is precisely known. In fact, this is a test condition. The subject actually knows exactly what the tone is. Suppose to know what the tone is. But you notice that this is a much shallower curve, right, than this human curve. Now we know that the horizontal shift simply means that the human is not as sensitive as the optimal ideal observer. But how do you explain this slope? Well, it turns out that one explanation for the steepness of the log slope is that if you assume that the observer is not monitoring just one tone, but there's an uncertainty in the observer. The observer is simultaneously monitoring multiple tones because the observer doesn't really know, or the listener in this case, doesn't really know when the tone starts, when the tone ends, or what is the phase of the tone, or maybe what is the spatial frequency of the tone. Now, if you allow number of orthogonal signals to be monitored by this observer, you will see that the slope, log slope becomes steeper and steeper and steeper. In fact, this one matches fast to approximately n equals 64. There's also another important manipulation here, which is that there is a psychophysical manipulation to give you a curve from humans that's exactly matched this. And that's when you're not doing a detection task, but you're doing a discrimination task. You're detecting an increment of the tone, the loudness of the tone. And nicely, all these auditory experiments have been replicated in vision, and if you measure in the appropriate units, they all match. So, now, and I think I have 37 seconds. Is this exactly 15 minutes? 15 minutes. Okay. Which I will not elaborate further on this reason, but only to say that if you really to make the following assumption, that is, a neuron will fire when it's telling you that it's going to detect something, and it wants to be somewhat reliable in that you want to avoid a huge amount of false alarm. Then the setting of the false alarm essentially is determined by the amount of signal uncertainty. Now, signal uncertainty is another word for invariant. Invariant simply means that you want to simultaneously respond identically to a whole range of input. So in a sense, an ideal observer in this case will have to be simultaneously monitoring multiple possibilities of the input. Okay? And this multitude of possible input will actually set up in such a way that your chance of false alarm is going to increase unless you adjust your criteria. So in this case, when there is no uncertainty, you can set your criteria low to have still a reasonable false alarm level. But when the uncertainty is very high, you have to increase your criteria. Right? Now, over this range so if you increase your signal strength, of course your performance is going to go better and better and better. Right? And in fact, in the linear scale, this is exactly the same range, roughly speaking, according to this model, but we don't have to rely on this model for the moment. So what you are seeing here is now you see this increase in log scale, you see this increase in log slope. Okay. So here is the summary of the line of reasoning, and I will end in about 30 seconds. Not exactly that. Okay. We make three critical assumptions to go through this line of reasoning. First, we assume that along a processing stream, there's an increase in feature invariance. And this feature invariance, indeed, is identical to signal uncertainty. So that means there's an increase in signal uncertainty. So now we appeal to psychophysical techniques. If we assume that the neurons have a roughly fixed false alarm rate, then we can make this assumption. That is, if you can measure somehow percent heat rate of the neuron, then the log stiffness of the neuron response function should increase as a function of increasing uncertainty. Okay, the last step is really the step of magic. Okay. Since we don't know the direct relationship between the firing of the neurons and both signal, we're willing to make an assumption that is they are somehow related by a power function. And the reason I choose a power function is that a power function therefore does not affect the ordinal of the ordinal relationship of the log slope. So hence I would predict as you march down a processing stream, the log slope of the both response function should go up, which is what we will see. So that's why we march up the processing stream, the log slope increase. And well, I don't think I have questions, time to defend myself on a few common challenge. So I will just conclude by saying that I think there is a way that functional imaging can be used to at least put in constraints about what area is talking to which area and how the way the decision flows. Specifically for this experiment, we show that the log slope of both signal with the signal to noise ratio increase along the ventral visual pathway. The slope did not differ from 0 for V1 and V2, but then it started increasing afterward. And this is consistent with a sort of a cascade of many-to-one classifiers that arrange in this following order. Thank you.
We have time for one quick question.